You want to learn to build fast electric cars, or robots that can run and jump, or drones that can zoom into the sky, then you need to learn electronics. But to learn electronics, you need to learn the basics of electricity. So let's go. Before you can buy your own fancy car, comes the hard work of learning engineering, C, and Arduino. I'm here to help. Before you can safely connect a LED, resistor, capacitor, or transistor to an Arduino, you need to understand what the electricity is actually doing. Why does the current need a complete loop? Why does the LED need a resistor? What does polarity matter? And how can one small Arduino pin control a much larger circuit? In this video, we will build the electrical foundation you need before wiring real Arduino projects. We will encounter ideas such as Ohm's law and components such as LEDs, resistors, and transistors. You do not need to master all of them immediately. For now, the goal is to understand what each component does and how it fits into a circuit. Electrical safety. Before working with electricity, we need to discuss safety. In this course, we will normally use 5-volt direct current supplied by an Arduino or a USB connection. 5 volts represents very little ordinary electric shock risk. But low voltage does not mean that nothing can go wrong. Never connect a breadboard or Arduino circuit directly to a household electric current. Disconnect the power before changing the wiring. Never connect the positive side of a battery or power supply directly to ground. That creates a short circuit. A very large current may flow, causing wires or components to become hot, very hot. A short circuit is what knocks the power off in your house. If anything becomes unusually hot, begins smoking, leaks, swells, or smells strange, disconnect the power immediately. DC and capacitor safety. Direct current is not automatically safer than alternating current. Most people think of alternating current as being the electric plugs in your house. This is true, and direct current is what we are dealing with when we are working with the Arduino, solar panels, or a battery. High voltage direct current can cause a severe or fatal electric shock, just as high voltage alternating current can. Electronic equipment may also contain capacitors. A capacitor can store electrical energy and may remain charged even after the equipment has been unplugged. The small capacitors we use in 5-volt Arduino circuits store very little energy. Large capacitors inside power supplies, microwave ovens, and other appliances can remain dangerous after power has been removed. Never open mains power equipment or attempt to discharge a large capacitor yourself. Electricity requires a complete path. Here the switch is open, the path is broken, so current cannot flow through the lamp. This is called an open circuit. Current travels around the complete circuit. When the path is complete, current can move around the entire circuit. It does not travel from the battery to the component and simply stop. The circuit forms a loop that returns to the power source. Engineers normally describe conventional power as traveling from the positive side of the power source through the circuit and back toward the negative side. The electrons in the external metal wire actually drift in the opposite direction, from negative toward positive. This is one of the great mistakes of history. The direction was defined before electrons were discovered. For the rest of this course, we will normally use conventional circuit, that term, when tracing a circuit. Okay, alternating circuit. A battery supplies direct current, or DC. Its polarity remains fixed. One terminal is positive and the other is negative. A generator works differently. A wind turbine, for example, is one giant generator. Inside the generator, magnets and coils of wire move relative to one another. A changing magnetic field produces a voltage in the wire. As the generator rotates, the direction of that voltage repeatedly reverses. When the wind blows hard, the blades rotate to reduce the speed and thus the electrical output. Too much electricity surging onto the electric grid will cause the grid to fail. Fail doesn't mean it breaks down. It means automated systems shut it down. The grid operates at 50 Hertz in Europe. That means the AC voltage completes 50 cycles in every second. In the Americas, it is 70 Hertz. The grid operators try to keep it extremely close to that target. This produces alternating current, or AC. In an AC circuit, the electrons do not continuously travel around the circuit in one direction. They move a small distance in one direction and then reverse direction as the polarity changes. Michael Faraday built the first device to generate electricity in 1831. We call this a generator. Faraday's first generator used a copper disc rotating between the poles of a magnet. As the disc cut through the magnetic field, it produced a small direct current. Faraday's early generator spun a copper disc through a magnetic field. Modern generators usually rotate a magnet or an electromagnet inside stationary coils of wire. As the magnetic field repeatedly sweeps across the coils, it pushes electrons back and forth, producing alternating current. Faraday made the first electric motor. It wasn't much. It pushed a piece of wire around in a beaker of mercury. But this was proof that electricity could create motion. Modern power stations still rely on this basic principle. Nuclear, gas, coal, hydroelectric, and wind stations use different sources of energy, but they generally use that energy to turn a generator. And Faraday created the generator. Elon Musk named his company after Nikola Tesla. The Serbian was perhaps the greatest electrical engineer of all time. He worked out ideas in his head instead of experimenting in a workshop. He was a theorist. He developed the polyphase alternating current systems, generators, transformers, transmission methods, and motors that made possible the systems of generation and distribution of power that we use today. He was a genius engineer, but not such a great businessman. He worked for Thomas Edison, but quit after 6 months. George Westinghouse licensed his patents and hired him as a consultant. But Tesla had already figured out how to light up cities. So he spent all his time trying to figure out how to transmit electricity wirelessly across the ocean from New York to England. And he terrified the people of Colorado Springs, Colorado, with his man-made lightning. His inventions are too numerous to list. They include the AC induction motor. Tesla's AC induction motor had a rotating shaft, but it did not need brushes to carry electricity into the moving part. A rotating magnetic field made the rotor turn, and his inventions led to the invention of the radio. The Italian Guglielmo Marconi said he invented the radio. But in 1943, the U.S. Supreme Court invalidated one of his patents, saying Tesla had invented that piece. A competition broke out in New York City between the American Thomas Edison and the Serbian Nikola Tesla. There was enormous money to be made wiring New York. Thomas Edison's company, General Electric, made the manufacture of cheap light bulbs possible. Other people invented the light bulb, but Edison improved it and used it and turned it into a business. But Edison wanted to use direct current to light up New York. Tesla correctly pointed out that direct current would require a generator every kilometer distance. Of course, that's not practical. So Tesla invented the polyphase alternating current to send electricity great distances, like thousands of kilometers. Tesla had no money, so he partnered with George Westinghouse to power New York. Westinghouse paid Tesla a royalty for every kilowatt, but those fees soon threatened to bankrupt Westinghouse. So George asked Tesla to reduce his fee. He reduced it to zero. If he had simply kept a fraction of what he had been paid, he would have been one of the richest men in history. James Clerk Maxwell was a Scottish mathematician and physicist. His equations are the most important in science, perhaps second only to Einstein's in fame and influence. They explain the relationship between electricity and magnetism. These are not completely separate forces, but two parts of what we call electromagnetism. Maxwell also showed that changing electric and magnetic fields could travel through space as waves. He calculated that these waves would travel at the speed of light, which revealed that light itself is an electromagnetic wave. Radio waves are another form of electromagnetic wave. Maxwell predicted their existence before anyone had actually produced or detected them. Don't worry, we will not attempt to understand these equations in this course. What matters here is that they describe how electric charges, electric fields, and magnetic fields interact. It's also important to note that he named these equations for the giants in mathematics and physics who came before him and whose work contributed to Maxwell's work. Carl Friedrich Gauss, Michael Faraday, and André-Marie Ampère. You probably have heard of an amp. An amp, short for ampere, measures electric current. It shows how much electric charge passes a point for each second. 1 amp equals 1 coulomb of charge per second. 1 coulomb is a certain quantity of electric charge. It is equal to the charge carried by about 6.24 billion electrons. The German Gauss's main contribution was uses math to describe how electric charge creates an electric field. Gauss was one of the greatest mathematicians of all times. Gauss was also deeply involved in the study of the Earth's magnetic field. Working with William Weber, he developed precise ways to measure magnetism. Polarity. Polarity describes the positive and negative sides of an electrical voltage. Some components are polarized, which means that their direction matters. A battery has positive and negative terminals. A lead has an anode and a cathode. The anode is positive and the cathode is negative. Some capacitors also have positive and negative leads. A diode is polarized. Connecting a polarized component backward may prevent it from working and can sometimes damage it. An ordinary resistor is not polarized. It can be installed in either direction. Voltage tells us how strongly electricity can push charge from one point to another. It always compares 2 points. The technical definition is the one engineers use. It's confusing, but I will give it anyway. The voltage is the difference in electric potential between 2 points. To make measurements easier, we choose one point in the circuit as the reference and call it ground, or 0 volts. Other voltages are measured relative to that point. The confusing point is the word potential. It is an abstract quantity defined only after choosing a reference. Ground does not always mean the physical earth. A connection to earth is called earth ground. Your house has a protective ground wire for safety. Suppose a damaged wire inside a washing machine touches its metal case. Without a ground connection, the case could become live, and the person touching it would receive an electric shock. The metal case is therefore connected to the protective ground wire. If a live wire touches it, a large current flows through the ground wire. This causes the circuit breaker, fuse, or safety switch to cut off the electricity. Grounding can also help protect electrical systems from lightning and power surges. although buildings may use additional lightning protection equipment for that purpose. The metal lightning rod is mounted above the building and connected by a heavy conductor to electrodes buried in the ground. If lightning strikes, the system provides a controlled path for the enormous current to travel into the earth instead of passing through the building and starting a fire. And yes, the lightning rod was developed by Benjamin Franklin, the famous American scientist, inventor, and ladies' man. Franklin is also famous for flying a kite during a thunderstorm. Contrary to the popular image, the kite was not struck by electricity. The storm electrically charged the wet kite string and the metal key attached to it. Franklin observed sparks in the key, demonstrating that thunderclouds contained the same kind of electricity the scientists had produced in laboratory experiments. That insight helped lead to the lightning rod, a way to protect a building by providing lightning with a deliberate path to Earth. When he worked in Europe as ambassador to France, Franklin went all over installing lightning rods. He liked the publicity. What is a capacitor? A capacitor temporarily stores electrical charge and energy. You need a capacitor when a circuit must temporarily store electrical energy or smooth out rapid changes in voltage. When connected to a voltage source, it charges. It can later discharge and release some of that stored energy. Capacitors are used to smooth voltage, reduce electrical noise, and provide brief releases of energy. Some capacitors are polarized and must be connected in the correct direction. Remember that tiny capacitors used in our Arduino circuits are very different from the large, potentially dangerous capacitors found inside other power equipment. What is a diode? A diode is a component that allows current to flow mainly in one direction. It has two terminals, the anode, which is the positive side, and the cathode, which is the negative side. A diode is therefore somewhat like a one-way valve for electricity. You could use this with your Arduino projects to protect against reverse polarity, stopping current from flowing backward into another part of a circuit, protecting a transistor from the voltage spike produced when a motor or relay is switched off, and converting AC into DC. The motor example is especially important. Motors, relays, and solenoids contain coils. When the current through a coil is suddenly interrupted, the collapsing magnetic field can produce a large voltage spike. A diode placed across the coil gives that current a safe path and helps protect the transistor and Arduino. What is a LED? LED means light emitting diode. Because a LED is a diode, it has polarity. Its two leads are not interchangeable. When the current passes through the LED in the correct direction, it produces light. A LED produces light using a semiconductor. Different semiconductor materials release different amounts of energy, which produces different colors of light. This is very different from a traditional household light bulb, which heats a thin metal filament until it glows. They've actually replaced that old system with the new bulbs that we have because that one used too much power. The transistor is also made from semiconductor material, but it is designed to control the flow of current rather than produce light. So the semiconductor is the material. A semiconductor is a material whose electrical behavior can be changed by adding tiny amounts of other elements. In many electronic components, that material is silicon. Ohm's law. Now we add Ohm's law to connect voltage, current, and resistance. The formula is voltage equals current multiplied by resistance. Voltage represented by V is measured in volts. You can think of voltage as the electrical pressure pushing charge through a circuit. Current represented by I is measured in amps. Current tells us how much electrical charge passes through the circuit. It is measured in ohms. Resistance limits or opposes that flow. So when we know the current and resistance, we can multiply them together to calculate the voltage. For example, if a circuit has a current of 2 amps and a resistance of 5 ohms, the voltage is 2 multiplied by 5, which equals 10 volts. Voltage. We can also rearrange the formula to calculate the other values. Current equals voltage divided by resistance. And resistance equals voltage divided by current. We use different versions of this formula when, for example, choosing resistors and calculating how much current can safely pass through a component such as a lead. Okay, what is a resistor? A resistor is a component designed to limit current. It can also create a predictable voltage drop and convert some energy into heat. An ordinary resistor has no polarity, so it can be connected in either direction. In a lead circuit, the resistor prevents excessive current from passing through the lead. Without the resistor, the lead may become too bright, overheat, or burn out. The Arduino output pin may also be damaged. Okay, what is a transistor? A transistor is an electric component that can act as a switch or an amplifier. In this course, we will first use it as an electric switch. A basic NPN transistor has 3 terminals: the base, collector, and emitter. A small signal at the base controls a larger current through the collector and emitter. This allows a small output to control another part of a circuit. A transistor wired like this can also be a logic gate. We will see in other videos that these logic gates can do logic and arithmetic. By combining enormous numbers of transistors, we can build and will build a computer. Building a computer this way is what we do in my Arduino course. Transistors are made from semiconductor materials, usually silicon. Pure silicon is neither a good conductor like copper nor a strong insulator like plastic. Its electrical behavior can be changed by adding tiny amounts of other elements, a process called doping. Doping creates 2 useful kinds of material: N-type material, which has extra movable electrons. P-type material has missing electrons, called holes. A hole is not a physical particle. It is an empty place in the silicon structure where an electron could fit. When a nearby electron moves into that empty space, it leaves another empty space behind. In this way, the hole appears to move through the material like a positive charge. When p-type and n-type materials meet, they form a p-n junction. At first, some electrons from the inside move across the junction and fill the holes in the p-type side. This creates a depletion region in the middle, an area with very few mobile electrons or holes. The depletion region creates an electrical barrier that prevents most additional electrons from crossing. When we apply a voltage in the correct direction, the electric field pushes electrons toward the junction and reduces that barrier. The depletion region becomes narrower, allowing more electrons to cross from the NP-type side into the P-type side and fill available holes. A diode uses one p-n junction to control the direction of current. A transistor uses multiple semiconductor regions and junctions so that a small electrical signal can control a much larger circuit. A transistor uses multiple semiconductor regions and junctions so that a small electrical current can control a much larger current. Now, what I've just described here is the computer CPU. These things were invented in Bell Laboratories, which is the American Telephone and Telegraph Company, AT&T, for which Nobel Prizes were awarded. The transistor, the CPU, that is an entire story to be told in another time, but the transistor came out of Bell Laboratories, and then Fairchild Semiconductor and Intel turned it into the semiconductor, which put us where we are today. Massive data centers with computer chips. All that is what we're looking at now. We're looking at it from a point of view of a single tiny resistor, transistor, which you can buy for 3 cents. So anyway, thanks for watching this video. See you next time.